Okay. So, in the last class, we have been talking about transmission lines, and then we saw how Smith chart can help us to find out the different parameters or the distributed parameters of transmission lines. Okay. Today, what we will do is another extension of this. So basically, the basic idea about transmission lines was that the connecting leads or the wires that are there, they have an effect on the signal that is being transmitted, right? So now one thing is transmission lines, but let us see what other things can come up. So we'll be today talking about waveguides, and there we'll see how different waveguides are from transmission lines and what kind of modes or by modes we mean what kind of electromagnetic waves are supported uh, inside different waveguides. And basically this comes from the same concept of boundary conditions that we have been trying to solve, or that lies at the heart of this problems is the same boundary conditions that we always have to satisfy at the surface of different mediums, right? So basically the same boundary conditions will apply, and we'll see that will tell us what kind of modes or electromagnetic waves remain inside different waveguides, and how different are the waveguides from the normal transmission lines. So that is about today's mostly about today's class. And as usual, we'll discuss this concepts. We'll try to solve some questions. And if you have any doubt, we'll try to clear them. So now to start with, basically, this is something similar to what we have been discussing previously, right? So it's the transmission lines. And as you can see, you can have some signal, you can have some load. Okay, so it can be a complex one, like it can have impedance or it can be purely resistive, doesn't matter. But basically, there should be some load here, and then you have some source. Okay, and then you see that this is your transmission line, right? Now, when there is current flowing through this transmission line, we know that because of the current or the changing currents, there'll be magnetic fields that will be generated around this current carrying wires. And if the current changes with time, it will also result in changes of the field. But now, so what this is telling you is that there's a magnetic field associated with this connecting leads or currents, right? And then we also know that the voltage here is not the same as the voltage that we get here, right? That's the basic concept of distributed circuits, that they have an effect. So the voltage has a so it can attenuate depending on whether it's lossy or not. Otherwise, there can be phase accumulation that can come in. So the voltage here is not the same as the voltage here. And then what is exactly voltage? So voltage or potential difference is actually the integral of E dot dl, right? So basically there's a electric field difference that comes in. So there's an electric field that is involved. So suppose if you have this source connected here, so the positive terminal goes here while the negative terminal is connected here. So that means you'll have an electric field in this direction. And now if you have a current which is flowing like this, there'll be these magnetic fields that will be generated. And as you can see from the image, so if the current is flowing in this direction, you'll have the magnetic field in the y direction, right? If this is z and this is x, so the magnetic fields will be along the y direction. So now basically in that means in a transmission line, what you have is like a plane wave, right? So you have electric field, you have magnetic field, both of them are perpendicular to the propagation direction of your wave. So it's like a TEM mode. So transmission line supports TEM mode. But now what's fundamental in this transmission line is that you have two conductors, right? This is one conductor and this is another conductor. Now what happens if you have only one conductor, right? Something like this, where this entire surface is actually a conductor. Okay, and suppose normally if you consider a case where you have a conductor and then you have some current carrying wire going through it, then it's again same as having two conductors, right? But if you don't have it, so what I mean is, if you if you don't have this thing, right, there is no current carrying thing there, nothing is going in, no current carrying wire, only this conductor you have. So it's a closed conductor that you have got. So then it's a single conductor. And in that case, there is no source of uh, like this HY component, which or the magnetic field component that was coming from the because of the presence of this current carrying wire. You don't get it here, right? So what happens in those cases, right? So we'll see that this kind of single conductors are actually serve as a waveguide. So what do you mean by waveguide? It directs or guides the waves to propagate in certain way, right? So certain frequencies will be propagated, certain frequencies won't. So this structure and their dimensions would determine that. So this is called a waveguide, right? So if you look at the differences, what we see is that transmission lines are suitable till few gigahertz, 3 to 5 gigahertz and something around that range. But now if you go to higher frequencies, like if you go to some terahertz or some higher frequencies, then what you need is their transmission lines won't be that effective and will then need a waveguide. Okay. And how waveguide is different from transmission line is that here you can see there are two. So this is one conductor, this is another conductor. So there are two conductors that are involved. Here there's only one conductor that is involved. Okay. And as we saw here, TEM mode is supported. While you'll see that in waveguides, TEM modes are not supported and it supports higher orders like TE or TM modes. So what you mean by TEM? TEM means transverse electromagnetic modes, right? So because electric field and magnetic field both are perpendicular to the direction of propagation, that's why it's called a TEM mode. But there can be transverse electric or transverse magnetic modes, and that can come up in the waveguide. So we'll see how. Okay. So now coming to the concept of waveguides. So initially we saw that if you have some free space, so we know that there'll be so if you have to propagate some light in a free space, we know that it will travel in the form of plane waves, right? And the plane waves are essentially transverse electromagnetic waves. But now what happens when you put them inside this hollow pipe? So this is a hollow pipe, okay, and it's a conductor, and then you put it inside that. So what happens there? That's what is the question that we're trying to ask. Okay. Now, because it's a perfect conductor, that means inside this material. So in this material here, the electric field and the magnetic field should be zero, right? So now if you apply your boundary conditions, so basically what do you want to get? You want to see what kind of waves propagate through this hollow pipe, right? So what you want is you want to find the electric fields in this region. And you know that the electric field and magnetic field in this region, like in this internal, uh, so it might be a very thin hollow pipe, but that thickness of your conductor, there the field is zero, right? So that means in this boundary, what happens is you want to find the electric field here, right? You want to find the electric field here, and here it's zero, right? So now it's a boundary valued boundary condition problem. So you have to satisfy the boundary conditions, and that will come from the Maxwell's equations, which we all know. So now uh, what this is telling you is that, so what do? Your electric field here is, suppose let us take the magnetic field first. So magnetic field here is zero, right? Now what should be the magnetic field just immediately below? Obviously that should satisfy this condition, and this is coming from divergence of B being zero, right? That is coming from the Maxwell's relations. Again, we see that the tangential component of electric field should be zero. Okay, so how do you get it? Like from which Maxwell's relations are we getting this? So if you remember, we saw that curl of E is equal to minus del B del T. And now if it is not changing, then what happens is your curl of E becomes zero. So in that case, if you take a line integral, you would see that the tangential components should be zero, right? And even otherwise, if you take a very small pillbox, by that logic, you can say that the tangential components here on the inner wall, okay, that should be zero. So these are the conditions, boundary conditions that has to be satisfied in the inner wall. Now, free charges and currents will be induced on the surface in such a way. So this is the condition that has to be satisfied. So there can be free charges, there can be currents. So they'll try to induce and get distributed in such a way that this constraints or this boundary conditions are being satisfied. Okay. Now, suppose what we want is we want to find what kind of waves propagate in this region. So you take the general form of electric field and magnetic field, and this is how it looks, right? So it's a complex, as you can see, it's a complex amplitude that we have taken for generalization, and we consider that it's propagating along the z direction. So we take it as e to the power I kz minus omega t. Okay. So now the electric and the magnetic fields must satisfy the Maxwell's equations, right? And what are the Maxwell's equations? These are the Maxwell's equations that we have to satisfy. Okay. So now what we do is we break this, like we express this electric fields in terms of different components in X, Y, and Z. Same goes for the magnetic field. And what we do is we put it in our Maxwell's relations. So that gives us these relations which relate the different components. Okay, so where is my circle? Let me, sorry. Okay, let me shift to, okay. So what we want to do is we want to find this relations which relate different components of electric field and magnetic field, right? This comes directly from the Maxwell's relations. Now, from equation 2, 3, 5, and 6, okay, what this is telling you is you can write Ex, Ey, and Bx, By in terms of this components, right? So here you can see that Ez, Bz is coming up, right? So what this is telling you essentially is that now you do have a component in the z direction, right? If suppose your Ez and Bz are 0, like if you consider our normal cases of plane waves where electric field and magnetic field is perpendicular to your direction of propagation, that means Ez and Bz should be 0. But if you put that, what you will end up getting is everything being 0, right? There'll be no wave. So this tells us that in case of this kind of waveguides or cases where we put it inside a confined region, because of the boundary conditions, we do end up getting longitudinal components, okay? Components of electric field and magnetic field along the direction of propagation of your wave. Okay. And now if you know Ez and Bz, you can actually find all the other components. Okay. Now if you put this equations like this here to the remaining equation, which is this, then what you get is this. So this is you can see it's a, so this is similar to our wave equation concepts, right? So it's very easy to solve second order differential equations, and this will directly give you a form of Ez and Bz, right? So now if your Ez, so that means essentially Ez and Bz might not be 0. One of them can be at some point, right? So now if Ez is 0, then we call it a transverse electric. Why? Because that means your electric field is perpendicular to the direction of propagation of wave. Again, if Bz is 0, then we call it as transverse magnetic waves, right? For the same reason. And in some cases, if obviously this is a general case where both of them are 0, we call it TEM waves. There can be cases where both of them are non-zero as well. Okay. But so this non-zero longitudinal components come up only when you have this kind of confined regions or waveguides through which you want to propagate your electromagnetic waves. In free space, where you have infinite extent, there's no boundary conditions to be applied. In those cases, you do get plane waves, that is TEM modes. Okay. And TEM modes cannot occur in hollow waveguides. Why? Because if you put TEM, then Ez, Bz should be 0, then everything turns out to be 0. So there is no wave in that case. Okay. And now this is for a hollow waveguide when you have no wire in between. But if you have some current carrying wires in between, maybe, so suppose if you think of some coaxial cable kind of configuration or something like that, then it's like a transmission line. There you have two conductors. Okay. So there obviously like TEM modes do exist. Okay. This is the case where you have just one conductor which acts as a hollow waveguide. Okay. So now let us look at the transverse electric waves in a rectangular waveguide. So you have a waveguide like this. Okay, so these are the dimensions A and B. Now you want to find how, so we know that suppose we are told that you will get transverse electromagnetic waves. That means what? That means Ez is 0, right? Transverse electromagnetic, transverse electric fields, meaning the Ez component is 0, right? Now you want to find how the electromagnetic waves will be. So that means you have to find BZ, right? BZ is not known to us. So now in general case, what you can consider is BZ would be a function of X and Y, because so it's propagating along the Z direction, but it can be a function of this variables, right? So the most general thing that we do is we do write it as a product of variables, functions, and then you put the expression. So this is what this is this expression, right? This is this expression that you're using. Your EZ is 0. Now you're using this relation, right? And if you put that here, you get something like this. So basically, it's same as how you used to solve by separation of variables, right? So you write independent equations for X and Y. And then, and this is the relation which is to satisfy your wave vector definition. So now what you do is the general solution. So what should be the general solution of this, right? So the general solution should be something like this. If you just take the first part, like just for X, so this is a general solution that you are supposed to get. Similar would come for Y, right? So now suppose if we look at the solution for X, what we get is this, right? Here we'll apply our boundary conditions. Now as you can see, it says that the boundary condition required that Bx should, so Bx should be 0, right? And Bx meaning it involves dx, like the capital X dx. Why? How are we getting to this point? Is because of this expression. See, so what it tells us is this components should be this condition should be satisfied, right? And then that tells us that your Bx should be 0 on the boundary. Okay, and you can see that your Ez is already 0. It's a transverse electromagnetic wave, so this part does not remain. You have this term here. So you see that for Bx to be 0, del Bz del x should be 0, right? And you know this is how your Bz looks. So that means your for del Bz del z to be 0, this should be equal to 0. So now if this is your x, you do a derivative and you try to make it use the condition that at x equal to 0 and at x equal to a, it's 0. And that gives you this value of your kx and ky. Like this is for kx. Similarly, you have to do the same thing for y, right? So that gives you these values, and it's important to note that here it ranges from 0 to like all the integral values, right? So this is how your you can say longitudinal component of magnetic field looks like for a TE wave in rectangular waveguide. It's just for you to note that there are these two cost terms. So this shows that in TE modes, this is how it should look like. Okay. And you define it as TEMN. Okay. Depending on what you have here, what are the integral values. So now what you can do is, kx and ky, this is the relation that it satisfies. So from here you can find actually the wave number, right? And this is how it looks like. If you write for k number to be uh, you know uh, real, this quantity should be greater than 0. So that means when omega is less than this particular value, your wave number becomes imaginary, and then what you have is an attenuated wave. So that means with time it would attenuate and die down, right? So for a traveling wave, your frequency omega, angular frequency omega, should be always greater than this value, right? So that sets the cutoff for the particular mode, right? For particular TEMN mode, this is the cutoff. Below this value, it would not travel. It would die down. Above this value, it would propagate, right? And so the lowest cutoff frequency, lowest meaning what should be the lowest value here? So either put M or N, one of them uh, to be 1, right? And the other to be 0. That's your lowest mode. And now if you if you consider A to be greater than B, then the lowest mode should be where M is 1, right? So it should be TE10. So this is your lowest mode. So there are questions which talks about what should be the lowest cutoff frequency for a TE mode, and then we can check it for a TM mode as well. So for a TE mode, this is your lowest cutoff frequency, right? And you can see that it depends on A, which is the dimensions. Now it's important to note one thing here, that you would think that this is constant, right? C is the speed of light, so that means your cutoff frequency only depends on the dimensions. But is it true? No. Why? Because here what you are considering is that you have air inside, and so here you have taken the speed of or speed of wave to be as c. If you have some dielectric, some medium which with some other permeability and like mu and epsilon values to be different from the from free space, then what you would get here is that particular velocity of your wave in that field, right? So this c can be v depending on what medium you are in, right? Or what medium is there inside the waveguide. So that means in general, your cutoff frequencies would depend on the medium that is there inside and also the dimensions, not just on dimensions. Okay. Okay. So now what you can do is you can write the wave number in more simple terms. So what it tells us is if you know the cutoff, this is how your wave number will look like. Okay. And now what should be the wave velocity? So we know v is equal to omega by k. So if you do that, this is what you get. And this is greater than c, but it's not a problem because it's the phase velocity. The energy which can energy carried, that speed cannot be greater than the speed of light, right? But that is the group velocity, and this is how you find the group velocity, and you can see that this is less than c. Okay. Now this entire thing can be visualized in another way where you say that the propagation of electromagnetic wave in a rectangular pipe here, it's based on it comes from the same concept of total internal reflection, like light reflecting through mediums which are bounded by slightly rarer you can say medium. So what happens is, consider an ordinary plane wave traveling at some particular angle theta, so that defines what your wave number is. Okay. And then it's reflecting perfectly off each conducting surface. So if it reflects, then what would happen is, so that tells you how your wave numbers should be to form a standing wave pattern. So what would happen? It would go, it would hit back, again it would hit, get reflected here, again it would come back. So that would create a standing wave pattern with this values which comes from the dimensions, right? So this is another way of looking at the same picture of how this periodicity is coming up in your waves, or how the different modes are being generated. Okay. And meanwhile in the z direction it remains as a traveling wave. So why? Because there is no confinement in z, right? The confinement is in x and y. So that brings in this periodicities in the wavelengths of like lambda x and lambda y. Okay. While in z it's a traveling wave with the wave number given as kz equal to k. So this is how in that case you can write the propagation vector. Okay. And you can see that it has this dimensions of your confinements or dimensions of the waveguide involved. And then, so what should be the frequency? Frequency should be omega equal to ck. So that means this is how it's related. So it basically gets back to the same expression. So what it's telling you is that cos theta, this component, would tell you what is the effective value of the wave vector in the propagating direction, right? And that value will give you the velocity of your wave inside the waveguide. Okay. And so that's what is being done here. So you find the cos theta component of your wave number, and then c into cos theta is your velocity, the net velocity down the waveguide. Okay. And this is less than c. Now this is what I was talking about. Is so this is how you write it, right? This is your omega. So in terms of frequencies you can write it as something like this. But if you generalize, so this should be, what is c? C is 1 by root over mu naught epsilon naught. For any other medium, like for a general medium, it should be given as 1 by root over mu epsilon. So it does have the effect of your medium that is present here. Okay. So cutoff depends on medium as well as the dimensions of your waveguide. Okay. So now what happens if you have TM modes, right? So in case of TM modes, it's the opposite. So initially EZ was 0, BZ was non-zero. Now it's transverse magnetic. So BZ is 0, while EZ is non-zero. Okay. And it's subjected to the same boundary conditions. So if we go back, it's subjected to the same boundary condition here, right? So that means, what does it mean? That the tangential components should be continuous, right? And the tangential component should be 0 because in the interior of the conductor it's 0. right? So that tells us that actually Ez should be 0 at the boundary, okay? So again, by similar process of variable, like separation of variables, you can get this expression. So this is how it's function of x. Similarly, it would have a function of y, okay? But then you have to apply the boundary condition that Ez is 0. Why? Because the tangential component of electric field is 0. Okay, this is the condition that you are using here. Okay, in the last case, what you had used is this. Well, you said that Bx is 0, and then you use this relation. So that's why it has a derivative of Bz involved. But here you have the tangential components of electric field being 0. So that means directly what you have to do is you have to make this term to be 0. So you have to make x equal to 0 at the boundaries. Okay. And if you put that, so that along x, this it should be 0 at x equal to 0 and x equal to a. Okay. And that gives you the value of kx, and b becomes 0. Similarly, you can do the same thing for y. Okay. And if you do that, this is what you get. But now it's important that your value of m or n, it starts from 1. It does not start from 0. Why? Because if you put 0, then the entire thing becomes 0. Like Ez will become 0. Sine of 0 is 0. So that's why here your first mode would start with m equal to 1 or n, like m equal to 1, n equal to 1, right? That should be your lowest mode. So it's important to note that the lowest TM mode is 1, 1, because otherwise Ez will turn out to be 0. Now, similar process, if you follow the same process as we were doing here, you find, so now you know kx and ky, you put it in this in the definition of the wave number, and this is what you get, right? So from here, you can get the value of your cutoff, and this is how it looks like, okay? And these are the values of your wave velocity or group velocity. Now, the lowest mode, as we said, and if you find the ratio of the lowest TM frequency to the lowest TE frequency, it would be something like this. So it depends on your dimensions of your waveguide. Okay. So now, based on this, let us try to solve some very fundamental and simple questions. Is that, so now if you have a rectangular waveguide where you know how the dimensions are, so A is equal to 2 into B, and the cutoff frequency for TE02 mode is 12 gigahertz. Okay, so TEMN, so here m equal to 0, n equal to 2, and for that particular mode, the cutoff frequency is at 12 gigahertz. So it said that the cutoff frequency for some other mode, which is TM11, okay, how do you find that, right? So that's the question. So basically now what you have to use is, you know, A and how A and B are related, okay? You know this value. So try to use the definition or expression for the cutoff frequency of a particular mode given the value of m and n, okay? And obviously that frequency, that cutoff frequency will depend on your dimensions, right? So from there, try to find the value of B. And if you know B, you can actually find A. And once you know A and B, you can actually find the cutoff frequency for any mode, right? So that's how this should proceed. Can you try to solve it? Yes. Try solving it. So you need to use this relations, right? So suppose this is the relation. Now you are, in this case, m is equal to 0, n is equal to 2, right? This is what is given here. So try to put that. Rest is known to you. You know omega. So what you have to find is B. And once you know B, try to find A and then the cutoff frequency for this mode. So I see another person joining in. So this is a question that we want to solve. So I guess you know how to find the cutoff frequencies, right? Or how the cutoff frequencies depend on the dimensions of your waveguide and Like what is the expression? So if you know that, here it said that you know the cutoff frequency for a particular mode. You know this is how A and B are related. So you need to find the cutoff frequency for another different mode. Okay. So for your reference, this is how it's related. The cutoff frequency of a particular mode is related to the dimensions as something like this. So now you know your for your question, you know omega 0 2, right? So m is 0, n is 2. You know what is omega, so try to find b and then use the relation to find a. And once you know a and b, you can again use the relation, putting m equal to 1, n equal to 1, and find omega 1 1, right? So that's the question. So in your assignments or in this kind of questions, it can come up that whether this particular frequency will be propagated or not. So the basic point is try to find the cutoff frequencies. Anything below the cutoff frequencies will not get propagated. The one that is above the cutoff frequency will get propagated. Should I share the solution? Let me know once you are done, or if you want me to share. Okay, I'll share the solutions there. Okay, so you say it's 6 root 5. Okay, okay. So let's see what the answer is. Okay. So now this is how it's given, right? So you put the value, it's similar. So this gives you the value of B. So this is what is your value of B. Now, if you put this relation, you find the value of A, and then you put it in this expressions to get this. I think what you might have done is, did you use this relation that omega and frequency are related by omega f equal to omega by 2 pi? So this 2, did you miss that, or like, can you check where you went wrong? This is clear, right? This solution is clear. I don't know like what exactly, where did you miss it, but this is the clear to both of you, like, or is there a doubt? If is there a doubt, you can ask me. Yes, I'll consider that you can understand. So this is simple like question. Okay, so this is how it's to be done in general. Okay, so now, okay, typing something. I saw someone typing something, but okay, you can even unmute and tell if you have some doubt. You don't have to just type. Okay, so right. So now this is a general question. This is how you find the cutoff frequencies. Okay. Now, so based on what we have studied till now, is the waveguide a high pass filter or a low pass filter or a band pass filter or whatnot? What do you think the answer should be? This is conceptual question, right? It should be a high pass filter, right? Why? Because the waveguide has a cutoff frequency. Anything below gets attenuated. Anything above gets transmitted, right? Okay. High pass filter, right? Okay. Now, this is another question which says that, in some cases, what can happen is your frequencies can be degenerate. So the cutoff frequencies can be same for different modes, right? And those are called degenerate modes. Now, the question says that the degenerate mode, like which among the following are degenerate modes? That means there can be, so the same values of like different values of M and N can have same frequencies. Okay. And you understand, right? That's the meaning of degenerate. So now, uh, which among the following do you think can be a degenerate mode in a rectangular waveguide? So you have to again use and think of the expression of your cutoff frequencies and then see, right? Put the values of M and N and then see. So try to write the cutoff frequencies of TE and TM mode, write the expression and then see. So see, like, look at this expression, right? Look at this expression. This is the cutoff frequency, right? So whether it's a TM mode or it's a TE mode, it's basically same, right? One thing that we noted is that the lowest TM frequency and the lowest TE frequencies are not the same. Why? Because the lowest mode for TM is 1 1, while the lowest mode for TE is 1 0, right? But when M and N values are the same, okay, in that case, the cutoff frequencies would be same, whether it's a TM mode or TE mode, because the expression is same. If none of them are zero, then what happens is for TE and TM mode, the cutoff frequencies are the same, right? It comes from this expression. This is the same for both TE and TM mode. The difference comes when one of them is zero or when you have to find the lowest frequencies. Okay. But otherwise, if for the same value of M and N, the TE and the TM modes will have the same cutoff frequencies. Okay. So that tells us that here, this is your expression. They're the dimensions. And this is the same for both T and TM modes. So the answer should be this, right? But both of them has to be non-zero. M equal to 0, not 0, and N also non-zero, right? Not just M, right? Okay. So now what should be the cutoff frequency for a TEM mode? We read about TE, TM. We did about TEM in transmission lines, right? Now, based on what we discussed, what should be the cutoff frequency for a TEM wave in a waveguide? Any idea? Think of what do you mean by cutoff frequency? Below the cutoff frequency, it gets attenuated. Above the cutoff frequency, it propagates, right? Okay, you say infinite. Okay, so cutoff frequency is infinite. So what do you mean by that? So if you say that the cutoff frequency is infinite, that means all frequencies, like TEM waves of all frequencies will get propagated, right? That's what infinite means. And okay, and you say zero. Zero means that none of the TEM waves will get propagated, right? That's the two answers. So two extremes I have got. One is like all the frequencies of TEM wave will get propagated, or none of the TEM waves will get propagated, right? And now let us, in order to see which one is the answer, let us just look back into what we were discussing, right? So what we saw is that in case of waveguides, something like this, so what do you need for a TEM wave? Okay, so you say number 3 is right. Okay, so let's see what is right. Okay, so what do you mean by TEM wave? TEM wave means that if your wave is getting propagated along Z, that means there should be no electric field component along Z and no magnetic field component along Z, right? Both should be zero. So EZ and BZ should be zero. That is what we mean by TEM wave, right? Now, from the boundary conditions and applying the Maxwell's relations, this is what we saw, right? Now, what happens when you put both EZ and BZ to be zero in these expressions? What do you see? So this tells us how you can, EZ and BZ, these values, if you know EZ and BZ, you can actually find all other components. Now here what you say is EZ and BZ is zero because it's a TEM wave, right? So what happens to EX, EY and BX, BY if you look at these expressions? This is directly from the expression you can get it, right? EZ0, BZ0. So what happens to EX? Zero. Now again EZ, BZ zero. So like if you look at it, what would happen is all these components are zero, right? You can also look at it from here, right? So if your BZ and EZ are zero. So basically what is happening is that there are no waves. You can also get it from this relations, but practically what we found is that there are no TEM waves in a hollow waveguide, right? So that's something which we found here, because like physically, if you think, in order to have some component of current in the y direction, suppose if your propagation is along Z and you have some voltage differences which come along the transmission line, that gives you a electric field. So you get an electric field which comes from the source here. But then in order to get a magnetic field in the perpendicular direction to both electric and propagation direction, if you want a magnetic field, you need some current carrying something, right? But if you have just one single conductor, you don't have that. So that, like physically, if you think of it, then there's no source of H there, right? Or if you have H, then there'll be, like, if you just look at the other side of it, like slightly differently, you would see that there would be no electric field. So basically what it's telling you is that waveguides do not support TEM waves, right? So now waveguides do not support TEM waves. That means whatever be the frequency, TEM waves won't be propagated, right? So the cutoff frequencies for TEM waves will be, now what do you think the answer should be? Right. So do all of you agree? When you, I think you also agree, right? because the cutoff has to be 0, because that means whatever be the frequency, it won't get propagated. If it is infinity, that means everything will get propagated, right? So for any waveguide, hollow waveguide, the cutoff frequency of TEM wave is 0. Okay. So yeah. So right. Okay. So now this is another part of, so that was about waveguides. In most of the cases, what I saw in your assignments, and it mostly based on finding the cutoff frequencies and checking which frequencies are propagating and things like that. So that comes from whatever we have discussed so far. Now, uh, talking about pulse on transmission lines. So this is another section of transmission lines problems that we were trying to solve. So basically now what it is telling you is that you have some load. Consider that for now it's a resistive load. And then you have the source here, okay? And in the source, what you're doing is you're giving pulses to your circuit. Okay, so you have a pulse source here. And then you're at the source side also there'll be some impedance, some resistance that is given as RS, right? And then there can be some reflections depending on what the characteristic impedance of your transmission line is. So depending on whether they match or not, you'll get some reflections at the load side, and you will get some reflections on the source side or the generator side, right? So that is given by this reflection coefficients. So in general, they are not 0. So that means there can be multiple reflections from this end and also from this end, right? So if that be the case, you send a pulse, right? And what in general a pulse is, so this is something which is also discussed in your course classes. So you can consider this pulse as a combination of two signals. One is some V naught. So if this is V naught, then some V naught pulse with like step potentials which starts around t equal to 0, right? And then depending on the pulse width, if the pulse width is some capital T, at time t equal to capital T, you have another pulse which is given by this. So you get a minus V naught pulse which starts at t equal to capital T. So what happens is and this continues, right? So after this point here, this signal and this signal cancels each other. They are of equal magnitude. So what you get then is back to a pulse signal, something like this, right? So that's how you can consider a pulse signal to be. So that means what you can tell is you can break a pulse into two kinds of waves. Okay, two-step waves. Okay, so now based on that, this is I'll directly discuss this question, which was also discussed, and I think this will give you a complete flavor of how this works. So this tells us that suppose if you have some non-zero reflection coefficients at the load end and at the generator end, and the pulse widths are given, and you know what is the voltage that you are providing, okay, from the generator, and you know the length of your transmission line, you know what is the speed of your wave, okay, and you know the delay. So the delay is like how much time it takes for the pulse to reach that particular length L. Okay, it's important to note that in this case the duration of your pulse is smaller than the delay. Okay, so now given these facts, okay, and it's said that RL or your load resistance, so the load resistance at this end, that is 100 ohms, suppose. Okay, so now what this is telling you is based on this RL value and your reflection coefficient value, you know what is gamma L, right? It's RL minus R naught by RL plus R naught. You can do that, right? You know the definition. So you know the reflection coefficient, you know RL. So by that, you can actually find the characteristic impedance of your transmission line, right? And that turns out to be R naught, and that is equal to 50 ohm. So you can do that. You can do, if you know the reflection coefficient, you know RL, you have to find R naught. So you can do that. Now, once you get R naught, this is your characteristic impedance of your transmission line. Now, you know the reflection coefficient at the generator end, right? So now, again, if you use this relation, you can find what is your resistance or impedance at the source side, right? So by using this relation, you get this value of your like resistance at the generator. Okay. So now that you know all this and you know that you're applying 12 volts, so what you do is you want to find what is your forward propagating voltage and what is the deflected voltage, right? So in order to find the forward propagating voltage, what you do is, 12 volt is the total voltage that you are providing. But obviously, because there's a mismatch, it's not completely matching, like the resistance are not matching. So there'll be the entire 12 volt won't reach here, right? So what would happen is there'll be a drop. No, even if it matches, so it gets divided in that case. So it's basically um, just a voltage division that's happening, right? So if you do that, you find what is your forward voltage that you get along along this points, okay, and that is 8 volt, okay. Now that means this is the voltage that comes up along the transmission line. So this is what you get. This is the voltage at between these 2 points, okay. So now if you know that, you can also find the voltage in the what is the reflecting voltage. How? Because you already know the reflection coefficient, right? So if you use that, this is the reflecting voltage. So basically it is reflecting from the load side. It's important to note that it's something which is happening at the load end. If V plus is here, then how much of it will be reflected? So that you find what we get here is that, so you have this light, okay. This is the time. This denotes time at z equal to 0 with your source. This is line at z equal to L, which is your load, okay. And you say that you apply a 12 volt pulse, and then what reaches at the load is 8 volt because of this voltage impedance differences, and this is what you get, right? This is what happens at the load end. It's important to note that it reaches the load at 0.3 seconds because that's the delay. Okay. Now at this point, so this is for the starting point here. So at the signal that was there at t equal to 0 here will reach here in 0.3 seconds, and the voltage will be 8 volt, right? And then a part of it will be reflected, right? And that is given by this V1 minus, and that is given by 8 by 3 volt. So this is what again gets reflected, and it again takes 0.3 seconds to reach the source side, right? Now again from the source side, what would happen? From the source side, there'll again be a reflection, right? And we know the reflection coefficient at the source side is given as minus 1 by 3. So that means this was 2.66. No, this is positive, right? This was because the gamma L is 1/3. Now gamma G is minus 1/3. So what happens is what goes back from here is minus 8 by 3 into 1 by 3. So it's minus 8 by 9. Okay. Now again here, what happens? Again, you use this reflection coefficient value. So it still remains negative because the reflection coefficient itself is positive. So it's minus 8 by 9 into 1 by 3. So it's minus 8 by 27. So that again gets reflected. So that's how multiple reflections would happen. Now that is for the signal that has started at t equal to 0. But your pulse width is given by, is 0.1 second. So that means you can break the pulse into two signals, one which is at t equal to 0, one which is at t equal to 0.1, right? Now this signal will again take 0.3 seconds to reach, and like all this will take 0.3 seconds. But what happens is now it's opposite, right? So what we saw is at this point, it's the minus of what we had here. So then the signal that will propagate is minus 8. This is minus 2.66. And this is 8 by 9. Again, here what you will get is 8 by 27, right? So that's how this is propagating. So if you want to draw how the pulse will be propagating, it's something like this. So at 0.3 to 0.4, you would get a pulse. How much will be the amplitude? It will be 8 plus 2.66, right? So if you do that, this is your pulse width, because 2.66 is something which starts from here and then it reaches in around 0.6 seconds. But from 0.3 to 0.4, the signal that you are getting is the summation of these two, and that is 10.66. Now again at 0.9, what happens is you get another signal which includes minus 8 by 9 and minus 8 by 27. So if you sum up that, you will get minus 1.18 volt. right? Similarly, it would again decrease. So you'll get this kind of pulses, and with time, it would die down. So basically, in case of, if this kind of things happen in your circuit or in your system, it's not a good thing, because you can see that, this, because the delay time is greater than your pulse width, it's dying down, and that the signal is lost. So basically, what's things would be different if your pulse width is much greater or larger than your delay time. Okay, so now the questions that you have in your assignment is mostly based on this concept. So these values would be, I think these values are the same in your questions, but then they're asking for something else. Maybe the pulse width is changed, or you have to find some value somewhere in middle, something like some other time value or something like that. But the main concept is how this is being described here. So that's all. Okay, so thank you. Do you have any particular question? Then we can try to address that. Okay. I believe there's no question. Do you guys have any question? Okay. So thank you. I think I'll write to NPTEL about the next class. Maybe next class I won't be able to take it on Tuesday. I'll be traveling. So most probably that's the case. So I'll try to uh, inform NPTEL about it, and maybe you'll get some mail regarding that. So just a heads up. Okay. Or if things are not as planned, then we'll have a class. So I'll inform NPTEL. Okay. So yeah. Thank you. Okay. Thank you.